Hey, can I start? So, good afternoon. Welcome to lecture 8 on thermodynamics of materials. Today, I will pick up that reversible and irreversible process. It's continued. One thing before I take up constant pressure, reversible, I demonstrated constant pressure, reversible and irreversible, but I will pick it up soon after I give you some easy way to recognize or easy way to understand whether explain why an irreversible process cannot be reversed. Easy way, you follow me. So with the help of this let me finish first, then I will pick up constant pressure. Okay. So this you follow isothermal. This may be easy way to identify, to know why an irreversible process cannot be reversed. Okay. So isothermal, the one that I am currently considering upon. What is this? Follow. This is forward. Let me write. 1A2 is what? 1A2 reversible forward. Forward means what? It is what? Expansion. Expansion, work done by system and positive all go hand in hand. So expansion. Gas expansion. You understand? Then what is 2A1? Tell me. 2A1 irreversible. Very sorry. Reversible backward. Backward. It is compression. Compression. Okay, 1A2, 2A1. Then what is irreversible? I showed you. There are many options. One easiest option is what? Okay, let us finish this, complete this. P1 V1T to P2 V2T, no harm. Then what is the irreversible? Recall. Or you call this double arrow maybe to distinguish it from reversible, and dotted line of course distinguishing. So this is 1C2 maybe. So let me write somewhere below here 1C2. Tell me what it is. It is irreversible forward, and of course expansion. Once more, right? And then what is this? You could recall what I said. This would be this up. You give a name 2D back one, irreversible backward path, compression. In the figure you clearly see that reversible path is retraceable. It has been retraced. I use backtracking, perfect backtrack. 1A2, 2A1. Hence the name reversible. I demonstrated why. Okay. So there is no argument on this. Irreversible system can be returned to the original state. Say 1 to 2, 2 to 1. System is returning, but surrounding is not. And in other words, there is no backtrack. Perfect backtrack. Why? This has been 1C2. It is not 2C1. It is 2D1. Now, why this happens? Easy way to appreciate this. I tell you. Follow. Expansion 1A2 reversible. To be an irreversible, it should be finite driving force. It is infinitesimally small driving force, namely dP. It is finite, like P2, P1 minus P2, such thing. So when you sketch this curve, irreversible forward, it should be anything below reversible. It should be a curve that lies below reversible because finite, lower than dp is delta p. Anything, just lower. It cannot be dp. So it should always be low. And see the opposite. When it is compression, it is going to A1 reversible, but irreversible in comparison finite driving. So at any value higher than this. Any value, so the position will be above this curve because pressure would be higher. Okay, here dp increase, no, delta p increase, which has been P2 to P1, that is the delta P for compression. So here dp, but it is delta. So what is the status? So this irreversible compression backward would be a curve which lies above reversible, leaving the backward, and the forward below. If one is below, another forward in principle by definition. So they cannot be retracted. They cannot retrace the path. There is no perfect backtrack. Easy way to put the argument. Easy way. So this part actually was pending, and actually I have finished now. Now take up. So next topic. So now consider. I think you have understood this. Any difficulties? Easy. One line answer. Why the irreversible process cannot be reversed? In the sense, in totality. Totality means both system and surrounding. System can be, but surrounding cannot be. How will you actually observe this from this? How will you justify this? This forward path and backward path will not be actually a perfect backtrack. Okay, so it will be different curves. Okay, one is below, another is above the reversible path. So this I said is we now consider constant pressure. Constant pressure, reversible and irreversible. Now this I discussed yesterday. This is the problem when you actually could not complete a topic, then you have to sketch everything. So I am demonstrating how constant pressure quickly, since I introduced this constant pressure reversible and constant pressure irreversible. Some inferences will be made quickly. So this is the constant pressure. Yesterday, since I discussed, I should go a little faster. Since constant pressure, it will move from state 1 to state 2 in the reversible fashion and the irreversible fashion. Let us do one by one. Suppose starting is pressure it is what? P, B1, T1. And this is P, B2, T2 being constant pressure. And what is the load? That is surrounding load. Okay. And of course, you have to give a thermostat for demonstration purpose. What thermostat initially? Initial state T1. Quickly. Now you want to go to the state 2 reversible. Yesterday I showed what? You have a number of thermostats and infinite number of thermostats available in this room. Available with you. So you can do, you remove this T1 thermostat, take T1 plus DT thermostat and put on. Replace this. So T1 plus DT, so next. T1 plus DT. Then what? And then it will be, the result is there will be increase in volume because pressure is constant in fixed number of moles, so temperature is increasing, so corresponding volume change which will be of course a very small dB. This is I said last day dB, and this way it is proceed, proceed and proceed and proceed. So next is what? Tell me T1 plus 2 dt, T1 plus 3 dt, and continue. Last but one, T2 minus dt, T2 plus dt, and you should note that here, T2 is greater than T1. V2 greater than V1, obviously. Constant pressure process. Ideal gas means ideal gas, N moles, etc., all given. Mine. Oh, who is calling? No, I'm confident. Hello, hello. For interruption. So start. So this way proceed to which state? Final. Final is, you know, this way goes to final state. Don't worry, you know. Recall the isothermal. Their pressure was changed. P1, P1 minus dP, P1 minus 2 dP. Final, etc. Similar. With the help of thermostat, there was mechanical interaction. Pressure change, mechanical interaction change. Here, thermal interaction with the surrounding. Difference. What is this? What is this method? What is this? Can I at this stage? Can I remove this part? I think it is actually not required anymore. So over. In fact, you actually, so to avoid confusion, remove all this. This part is over. Clear picture. So what is this path? Reversible. Irreversible will be what? Again start. Abruptly. So best abruptly give the final value itself. So one thermostat T1, take the T2 and replace. So this will happen. Now if you scale up, this I told you. Up to this point we discussed. Now I will give a sketch for this. This is a procedure demonstration. This is the corresponding plot on the PV plot, PV diagram. On the PV diagram, okay? This I am trying to sketch this plot. How will it do? Since it is a constant pressure, so it is moving from state 1 to state 2, reversible. First reversible. Reversible 1 to 2, okay? 1, 2. No problem. All states are through the infinite number of equilibrium states. Continuum of equilibrium states. Okay? See T1 plus dt, stop. Equilibrium. Stop. Equilibrium. Equilibrium. Expand. Equilibrium. 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 But movement. Process. Reversible process is an equilibrium process. So 1 to 2. Give a finite change. Irreversible in contrast is what? You know, since constant pressure is not violated for irreversible here. Here violation. So what in the previous diagram, what I said, how shall I draw? Irreversible. Okay. I should say through abrupt. So through it reaches there, but through non-equilibrium states. So this is the sketch. So how will I show you? 1 to 2, 1 to 2, reversible forward, forward, and what is 1 to 2? This one, 1 to 2 is irreversible forward. Dotted, irreversible forward. Now you want to take back the system to the original state, means initial state. How will you proceed? Tell me. So reversible. You want to get from state 2, get the system from state 2 to state 1, back to state 1. As we do, reversible to reverse. Then what is the technique? Then you start from this post. Oh, yes. Well, I'm sorry. This is missing. Last one is T2. Last one must be T2. Important. So it's oh, this was actually T2. So this is okay. So this is how you proceed. Start from this. That you apply this. So how will it look like here in this? Constant pressure, but it is a solid line, okay? You write here 2, 1, 2, 2, reversible backward. And what is the other one? Irreversible will be what? T2 to absorb to T1. So it will be again constant pressure. So it will be arrow this side. So this said, oh, the reversible irreversible I didn't draw the forward one. Reversible, irreversible forward, irreversible yellow, irreversible forward, irreversible backward. Reversible forward, reversible backward. So 4. Okay. This will be what? Reversible backward. Irreversible backward would be what? 1 to 2. Oh, sorry. Yellow being better. 1 to 2 backward. Irreversible backward. This is over. On the previous diagram, but difficulty is elsewhere. Difficulty in understanding something. I have said something beforehand, but you see something different here. For example, so you can put it. So reversible path is reversed, as it should be. The name we have explained. Reversible will be reversed. Can be reversed, forward and backward. Expansion, compression, if you may call this. Heating and cooling, better. Reverse. So reversible is reverse, no. Solid lines, no problem, sir. As before. Now you see, interestingly, irreversible is also reversed. Backtrack. Irreversible path is backtrack. But you said, sir, irreversible process path is not backtrack. They are different. I have removed this figure, unfortunately. This forward, backward. That was the idea. That is how you are distinguishing reversible from irreversible. But here, sir, you can say it is retracting. Reversing, retracing, backtracking, irreversible also. So how do you distinguish? Answer is this. Answer is, can I remove this? I remove this part. I have to use this one. Answer is PV plane you cannot distinguish. Consider TB plane. Then you will see the difference. Interesting observation. Let us draw this in the TB plane. These happenings, these processes, plot on TB plane. TB plane. I am plotting. Hopefully I'll be sorry. Let us draw nicely. TB plane. What is this? Just state 1. What is the reversible? This reversible occurrence on the TB plane. What? Temperature increases, volume increases, and they are proportional, linear relationship, straight line relationship. So draw this. Sir, no problem, sir. This is. What is the temperature? Tell me here. Can you tell me temperature? T1. Tell me temperature state 2, state 1. Right, state 1. 1. Right, 1. 2, state 1, state 2. So T1 is the temperature. What is the temperature up there? T2. So I have sketched nicely. And volume is what? In case you are interested, volume is what? B1, B2. You write this here. This is state 1. Right here clearly, state 1. Right here clearly. This is state 2. B1, B2. Okay, this is over. When you are reversing, what happens? Sir, interesting, no problem. Reversal, perfect reversal, as it should be. Back, again linear, reverse. Constant pressure. Now what will happen in this case of irreversible? If sketch the irreversible again with the yellow. Forward, irreversible forward. You sketch this. Yeah, it has already occurred. So no, nothing new there. Only presentation. So what happens? Tell me. I start state 1. What I did? Abrupt change. Abrupt change, sir. Do that, sir. Do that. Do that by all means. Change abrupt means instantaneous. Up, then also impact. Then there is an expansion. Increase in volume. This is the 1. If I may write here, state 1. Write 1, 2. Again, state 2 though. 1. Achha, 1A2, here also I give a name, 1A2 in the reversible. You will understand. This is 1A2, 2A1. This is over. Reversible is 1A2, 2A1. Here I should give a name, 1, 2, 1, 2, sorry, this 1 should be written clearly, 1. 2, what is the name? Path, tell me, 1. This is A is used up. 1, B2, irreversible forward. Right. Backward is what I have not shown. Yeah, it should be T2 to T1. Okay. What is the backward? A double arrow. Double arrow will be helpful. Yellow, double arrow, dotted, many ways. Back, irreversible back. What is? How you get it back? Get the system back to state 1. How? Here it is here. Abruptly T2 to T1. So down, compression, down, and then contraction, compression. What is the name to this? If you want me to, it is 2C1. Give double arrow for return journey, irreversible. I'm not writing this, you understand this is the, this actually, what is what, I don't, so you may write this 1B2, forward irreversible, and while 2C1 backward irreversible. Constant pressure, expansion or heating they call. Okay, heating or cooling. Backward is cooling, compression. Okay. This I will discuss later on. Constant pressure in detail, in further details. But this is part. Have they retracted? Retraced? Have they retraced? This is perfect backtrack? No, this is not this way. This. So it is demonstrated irreversible process cannot be reversed. Then the full statement would be this: reversible. You may write this: reversible process can be reversed. There is perfect backtrack of the forward path in all planes. What are namely? PV, VT, PT planes. All planes. If it is reversible, all planes. But it is irreversible, you will not see them in all planes. You may not see them. You will not see them. Why? Here you have seen. It is reversal. Retracing. But here in the TV plane, you have not seen. That means surely it is not reversible, it is irreversible. This is the thing. If it were reversible, it would, whether it is PV plane, whether it is TV plane, VT plane, does not care. This is actually the summary. So you can write this, okay. So you can write this. So reversible process, reversible path will backtrack in all planes, e.g. PV, VT, PT. Anywhere, any plane you consider. But irrev path will not backtrack. Backtrack means in the reversal. When you reverse it, don't backtrack in all planes. Maybe in some of the planes, maybe in some, by coincidence, as a PV plane it is backtracking, but not in all planes. This is the one message that I wanted to give you. Next is what I want to tell you quickly. Constant volume similar. So what? Another consequence. Can I remove this? PV diagram is very important to us. Why? I told you once, because PV diagram gives you the work done. Remember P external dV and such things. PdV, P external dV initially. So PV diagram necessary. Work done is a very important issue in thermodynamics. Work done. So PV diagram. So now I tell you what, you see interesting, W reversible, we see W reversible 1 to 2 is W irreversible. This is interesting. This is also interesting observation. So work done is area under the curve. Whether it is reversible, so forward, only forward, consider forward, not backward. That is over. Reversible process, reversing, etc. over. You have totally commented. now is work done. So work done in the reversible path is same as in the irreversible path. Why? Sir, area under the curve. This dotted though, area is area. So area is area, sir. But we had a notion that reversible work is greater than irreversible work. This notion I wanted to dispel yesterday. That statement, I do not know why it has been very popular across the world, that reversible work is greater than irreversible. But that is limited to isothermal and adiabatic. This I said yesterday. No. And clearly you see demonstration that now, yes sir, correct. In constant pressure process, in the constant pressure process. So that means not reversible is greater, equal. Another thing is this, and also in constant volume process. Constant volume I don't want to discuss much. The similar way, same way you carry out, same way you think about this, same way in constant volume process also. Constant volume, you know what happens? Yeah, state 1, state 1, state 2. State 2 is what? State 1 is what? Tell me. T1, B, constant volume, T1. And state 2 here itself, volume has not changed. State 2, P2, but with different configurations. P2, B, T2. So this, note this. First you note this, then I am writing something. Reversible or irreversible, this is the mode. Don't worry, this is the mode. No way. So I am writing. Also in constant volume process, I am writing something. Again same, equal. And what is their value? What are their values? Equal. Here equal you see, area under the curve. Area under the curve, 0. No volume change, P external volume change. It will be vertical line. It will be in contrast, if I may draw quickly. What is the area under the vertical line? And also concept key, no volume change. Your high school, no displacement, no here, no volume change. P external, dV out. So they are same, but in a strange way that both are 0. This is same, non-zero, same. So recall again once more, I am actually impressing upon you this statement that, so once more, note, yesterday I told you, maybe I will tell you today also, maybe tomorrow also, maybe later years also, that W, that famous statement, W reversible greater than W irreversible, for expansion though, for expansion, that is accepted, Compression is the opposite. Expansion, all done by system, This is greater. True for, tell me, isothermal and adiabatic. Not for constant pressure, does not hold good for, write this, does not hold good for, write this, finish this, for constant volume, constant pressure and constant volume processes. Note this, inscribe, wrote inside your blood, in your mind, in your heart, in your life, that I have demonstrated. If you have any objection, raise the objection here itself. Yes sir, no sir, you have wrong. Like say, I raise the question myself. Sir, retracing, then I clarified that yes, retracing on the PV plane, not other plane. Then you are convinced. Reversible will always retrace. What time? Time is anyone? Yes, teacher is waiting, so I cannot proceed. So before I stop.